Hello, my name is Bob D. Hilster and I am your particle model guru. This video is the fourth part of a series on light. This one is on dispersion. I did cover it in the second part, but it was kind of out of sequence, so now I bring it back. We're going to consider the following characteristics of dispersion by looking at the shape of the prism, the source of the light, the angle of incidence, phase velocity, and wavelength. I'll see how all these affect the dispersion of light, how it affects the amount that light turns as it enters the prism. So let's first consider shape. On the left is a rectangular prism, and on the right a triangular one, and doesn't appear to have dispersion here, but it clearly has dispersion through the triangle. So there seems to be a difference as to no dispersion and dispersion, or let's see. I did find this video, which is done by Ashish Arora, and it's a good one, which helps explain his explanation of what happens in a rectangular prism. And you're welcome to stop this video, watch this one, watch his video, and then you can return. In any case, now I move on. So if you watched it or not, one of the main points he made was that in this part there is a discoloration. So it's not quite pure white anymore, and he explains why and what's happening. So there is some dispersion here, just not to the same degree. Obviously it's the shape that has something to do with it that makes this disperse more than this, but refraction and dispersion both happen at the same time, and the shape and size has only gives you the amount of dispersion. Well, speaking of the amount of dispersion or refraction, I decided to look at take this chart and compare red to blue. Take crown glass, which has a index of 1.515, and for red, and for blue it has an index of 1.523. And then I did a calculation calculating the angle of refraction using Snell's equation. Red has a angle of refraction of 27.92 degrees, while blue has 27.56 degrees. Which gives a 0.36 degree difference between red and blue, and it appears that the refraction is greater for red than it is for blue. Well, that is true, because what I'm really interested in is the angle of deflection, which is 45 degrees off from this. So when you subtract the angle theta 2 from 45 and this theta 2 from 45, you still get 0.36 degrees, but then you subtract a smaller number from 45 and you get a greater angle of deflection. Now, if you have 7 colors inside this dispersion, you only have 0.05 degrees separation from the colors. It's very, very small. And so when the white light goes through the square prism, there's a very small difference. And the triangular prism, however, amplifies it. As you leave the triangular prism, it tends to be amplified since it's bent the same way. Okay, light source. In the particle model, the light is a stream of G1 particles. The stream has a high density at the peak, almost no particles in between, and again, a lot of particles at the peak. This stream, light moving to the right, is intended to represent in general red because it has a wide wavelength. And this one is intended to represent blue because it has a short wavelength. But the light source from nature is much more messy. I showed this last time. I don't think that a candle or a light bulb can issue these kinds of streams. They're going to issue something different. If these are just streams of the peaks, if I can just consider this peak and these peaks going through here in some random pattern, some of them may be spaced like blue, some red, some green, and in different quantities. You may have a stream of 5, 3, or 2. It's very messy, and if you watch my video on the candle and the light bulb, you'll see why I come to this opinion. Okay, so that's that, and we go to the angle of incidence. This is from a drawing I showed last time. The angle of incidence is here. I set at 45 degrees. The red light comes to the triangular prism, refracts and disperses, but in case of red, it's just one color, and then it refracts again and bends more. And what I showed last time was that the forces along each edge is about the same. It may be different in some ways, but it was hard for me to detect any difference. So, but in any case, I have a normal force in this direction, a G2 force, which can be broken up into a component in this direction perpendicular to the light stream, and then in this direction parallel. And this is the turning force. This is what causes this light at this point to refract 15 degrees. Because this is that first refraction, this is an extension of that. So this turns it, this causes it to accelerate. So if you increase this angle by moving the light over this way, you're going to get an increased force. If you decrease the angle, move it this way, you get a decreased force. Pretty much a one-to-one correlation between the angle of incidence and the angle of deflection or refraction. Now to phase velocity. When they measure phase velocity, they measure the straight line distance that the light progresses across the prism, and they divide it by the time delay, and they get the time delay, and this is just a generic diagram for phase difference. The top light stream is the incoming light to the prism. This is the outgoing, and there is a time delay between this peak and this peak. Not to belabor the issue, but in the particle model, there's a peak here, and there's valley here. There's no particles here, and there's lots of particles here. The wavelength I show moves the zero reference down here, so that you have double the amplitude of a number here and zero, double the amplitude and zero. Anyway, they use a straight line, but the particle model suggests that as the G1 particles go through the glass, it doesn't go through a straight path. And showing that path here, it should be going straight here, and it weaves its way through the glass just like an asteroid going through our galaxy. It would get attracted to one atom, then attracted to the other, and it goes through in some path. So it's longer. It takes longer. So you take a longer path, you divide it by the time, and you find that the speed in is actually equal to the speed out. So the phase velocity does not slow down passing through the glass, in my opinion, because of the distance it travels. Further, as I showed, there's a vector of the force that causes the particle to accelerate going in, and it continues to accelerate until this point in the middle, where the force vector this way and the force vector this way match, and there is no acceleration. And so the speed increases and increases, and then it decreases and decreases because it's still going this way and the force is slowing it down. Overall, there is no speed. Overall, there is no speed increase. Even from edge to edge, the speed is the same. Now let's take a look at the wavelength. That brings in an interesting point. Now I'm going to look at two peaks going through, moving in this direction, and the force vector is strongest when you're closer to the prism. It's weaker here, so there's a stronger force here causing this one to accelerate more than this. So when the leading one accelerates, it gets wider. When the trailing one accelerates, it gets narrower because this one's going to catch up to that one. And you got just the opposite this way. Even though they're going this way, the speed is generally going this way. Here you have the trailing one slowing down more than the leading. This is the leading one trailing down more than the trailing one. But in any case, it gets narrower. Here the trailing one is slowing down more than the leading one, and it gets wider. In general, from out here to out here, the wavelength is the same, but from edge to edge, interestingly enough, the wavelength gets shorter in both halves. So generally there's a blue shift inside the prism, and that may have something to do with the dispersion, because the stronger forces are going to cause a bigger blue shift. The weaker forces are going to cause a lesser phase blue shift. That can add to the dispersion, and I'll get to the force vectors next. Force gradient. So now we're going to look at the number of G2 particles coming into this system. It's an isolated system. The number coming in here and the number coming here and here and here, they're all the same number of G2 particles coming in. And of course, this is G1 light stream. This is G1 light stream coming in. I'm going to take a look at these two peaks of light, which start up here and move down to here. Now, as the G2 particles move through here, there's a loss, so this vector is shorter, and there's loss here. So this is less. This is not reduced. There's nothing lost here, so there is a net force here. And I'm calling it stronger because when you evaluate this, you've got the same vector here as here, but the number of particles here decreases significantly. And I say significantly because in general, when you have a large number of G1 particles in a stream of light or in a electrical circuit, a G1 particle replaces the electron, and you've got lots of G1 particles flowing through the circuit, you get a stronger effect on the G2 force. You're going to lose a lot. Whether you use a lot or a little, in any case, this force becomes weaker by the time it gets here. There's fewer particles, so the force is less. So this is weaker, this is stronger. Stronger on the right, weaker on the left. And it doesn't matter whether this is red, green, or blue, or white. Stronger on the right, weaker on the left, and has a gradient in between the two. Okay, so a low density causes less loss of G2s, and a high density causes more loss. But I'm talking about density because I'm going to use the idea that blue has a linear density that is higher than red. There are more particles per millimeter, if you will, in blue than there are in red. So the density, linear density, is greater. Hence, blue light in general, a band of blue light is going to have more G1 particles flowing through it than red does. So now I'm going to use that, excuse me, to move the two peaks up here basically the same drawing, except I got the loss this way and the loss this way about the same. So, but in this side, where this is generally stronger on this side and weaker here, I have more loss, and so this is even stronger because there's loss here that's not here. This becomes stronger. On the other hand, this has more loss here, and it becomes even weaker than when I analyzed it down here. So again, strong force on the right, on this side, weak force on this side. When you consider these two, now I'm going to consider blue. If blue is a higher density, then I'm going to have more loss than red. More loss means more force. So blue has more force. Red means less loss, means there's fewer particles pushing up this way. Fewer particles pushing makes, there's less loss, so there's more particles, there's more particles there. As a consequence, you have less force. More force on blue, less force on red. Regardless of whether this is red or blue, this is weaker than this one. And I'm going to use that in my next picture to show how we get red and blue dispersion. Looking at this, the right side where it's stronger, blue bends more here and blue bends less here. Red bends less than blue here, but this bends less than the red. And when you extend these lines out, you get kind of convergence of red focusing on a distant point out there and blue out there, and you end up with red here, blue red there, and blue here. You get a form of dispersion because of that force gradient. And if you add green, then green bends. This is still stronger for green, but it's lesser for green over here. But green is in between red and blue, and so it fits there. It'll have its point pointing out this direction. And you have red. Here's green, red, blue, green, red, blue, green, and blue, and so you end up with red, green, and blue out here. You have blue, red, and green dispersion. Now this is a special case. I admit it's a special case where I'm considering solid red, solid blue, solid green, and light's not that way. Light is not that way, and if I had to try to explain it here, yes, up here it's stronger, up down here it's weaker, and and all of these are going to bend more, and what's the typical loss? This is going to be weaker because there's loss up here anyway. So that the concept that this is stronger and this is weaker and that there's a gradient is still there. It's just hard to imagine how it bends red less in total and blue more. It's just hard to visualize. Okay, in summary, the amount of light that turns at the edge depends on the shape of the prism. Yes, as it enters this rectangle, the shape does seem to affect the amount that it turns. The source, yes, the density affects. The source of the density of the source affects how much it turns. Angle of incidence, clearly. Phase velocity, standard answer, they say yes, that's what causes refraction, is the fact that the light slows down. I never see a physical explanation. I see equations for velocity. You'll see sine of the angle to the sine of the angle, referencing the phase velocity to the phase velocity of the two media. There's the equation, but no physical explanation. My answer is no. Phase velocity is slowed down, has nothing to do with it. The wavelength, yeah, they say the wavelength does, and I say, yeah, the wavelength has an effect because it includes density. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I will explain more of the universe using the particle model. Thank you for your attention.